Now let's look at how we can find equilibrium concentrations from the equilibrium constant K. So let's consider this gas phase reaction: nitrogen plus oxygen in equilibrium with nitric oxide. And let's look at the equilibrium constant in terms of concentration. And so we'll have the concentration of the product squared divided by the concentrations of the reactants. So that's our equilibrium constant. Now what we want to do is find the concentrations of the reactants and products at equilibrium. To do that, we need the equilibrium constant value. So we'd have to look that up in a table or be given that. And in our case, this equilibrium constant value is equal to 0.1 at a particular temperature, and that temperature is high, 2000 degrees centigrade. So now we have the value of the equilibrium constant. So we have three variables in this equation. However, their ratio constitutes a particular numerical value, the equilibrium constant. So what we can do is define an extent of reaction. Now this is the important part of working these equilibrium concentration problems. So we can do it three ways. I'll do them all three. Any of them is fine though. So we'll let a variable x equal to the amount of, say, one of the reactants into that reacts. Then we express the equilibrium concentration of all species in terms of that x. So if we have some mixture of nitrogen, oxygen, and nitric oxide, the reactants and products, we can say that at equilibrium we have the following concentrations. The concentration of nitrogen at equilibrium is equal to the amount we start with, and I'll signify that with a subscript 0, and that's just initial concentrations. And then I've defined the extent of reaction as the amount of N2 that reacts. So X amount of N2 will react, so the initial concentration of nitrogen will be reduced as some of it reacts. So we subtract X amount from the initial concentration. The concentration of oxygen at equilibrium is equal to the initial amount, and then we're going to relate it to X, the amount of nitrogen that reacts. But if we look at the balanced equation, there's a 1-to-1 ratio between nitrogen and oxygen. So for every one nitrogen that reacts, one oxygen also reacts, and so the amount of oxygen that reacts is also equal to X. Now, the equilibrium concentration of the product, nitric oxide, is going to be equal to the amount we start with. Now the reaction is forming nitric oxide, so this is going to be an addition all amount, and so We see from the balanced equation that if one nitrogen reacts, two products, nitric oxide, are formed. So 2 times X amount of NO is formed during the reaction. So this is how we can create a variable X, letting it be an extent of reaction, and then express the equilibrium concentrations in terms of that one variable. Now we can substitute back into the equilibrium expression, and if we know the initial amounts, we only have a single variable, X, and we can easily solve the equation for X. Now what if I let X equal to the amount of NO product that is formed in the reaction? I can create an equilibrium table just in the same way. So the concentration of nitrogen, concentration of oxygen, and the concentration of NO all at equilibrium. So since I've defined X relative to NO now, I'll just say that the equilibrium concentration of the product, NO, is equal to the amount we start with plus X. X is now defined as the amount of NO that's formed. Now we go up to the two reactants. Say for oxygen, we start with an original amount, an initial amount, and some of it's going to react. And if we look at the balanced equation, we see that for every 2 NO that are formed, only 1 oxygen reacts. And so for every 1 NO that's formed, only a half oxygen reacts. So we would have 1/2 X subtracted from the initial amount. And the same thing for nitrogen, because for every 1 nitric oxide product that's formed, only half that of nitrogen reacts. So then we can substitute that into our equilibrium expression. We'd solve for X. We get a different numerical value for X, but the equilibrium concentrations that we calculate using this table above would be exactly the same as the previous example. It does not matter how you define X, the extent of reaction, as long as you are consistent in describing the equilibrium concentrations of everything in terms of your variable X.